Hi everyone, I'm Professor Adam Burgaster, and in this video we're going to be talking about some of the key math skills you need to develop in order to succeed in the Physics 1A course. And so we're just going to summarize some of the basic math that we'll be using frequently in the course. Some of this may be review, and some of this may be new. If any of this is new to you, make sure you take some time to go back and review these concepts in greater detail, because we're going to do just sort of a very rough course overview of what's important. The first thing that's important is to make sure that you know your trigonometry. We'll be doing a lot of examples where we have some kind of angle that we're trying to evaluate. And it's important to remember our trigonometric relations when we're talking about angles in all sorts of geometry problems. And so in this kind of figure, we can label the sides here based on their relation to the angle. The side that's closest we commonly refer to the adjacent angle. The side that's opposite that angle is, not surprisingly, the opposite. And the long end of this right triangle, and I should make sure I make that clear that this is a right triangle that we're drawing, is called the hypotenuse. Now, why do we care so much about right triangles? Well, when we're breaking down our coordinate systems, we often look at orthogonal coordinate systems, that is, coordinate systems where the axes are at right angles to each other. And so a triangle provides us with a right triangle provides us with a map on how we map angles onto these coordinate systems. So we have trigonometric functions that relate the sides of these triangles to this angle, and these are the kind of trigonometric relations that are important to remember. And so the key ones that we'll be using in this course are the sine of an angle, cosine of an angle, and the tangent of an angle. And these are related to this right triangle as just the ratio between these different sides. So I'm going to shorten my syntax here to have A as adjacent, O as opposite, and H as hypotenuse. Then we can define these quantities as opposite of hypotenuse for the sine, adjacent over hypotenuse for the cosine, and opposite over adjacent for the tangent. And a good way I like to remember this relation is this kind of acronym SOHCAHTOA. All right, sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. All right. Hopefully you've seen this before in your high school classes. But this is a good way to remember these angles. And also keep in mind that we have a relationship between these different sides because it's a right triangle. This is the Pythagorean theorem, and that's that the opposite squared plus the adjacent squared is equal to the hypotenuse squared. Now, when would you use these kind of relations? Well, for example, if we're looking at the geometry of a system that's on an inclined plane, in which case you're going to be oriented in a different direction from the gravitational acceleration vector, then you need to actually relate the forces that are along the edge of the inclined plane versus those that are perpendicular. That's a good place where angles are going to be coming into play. And the Pythagorean theorem, of course, is a good way of measuring the lengths of vectors when you know the components of those vectors along different axes. So all these relations are going to be used in our course. Now, the other thing to remember is how to evaluate these functions, not just in terms of drawing a triangle, but also in generally how do we look at how sine and cosine varies with angle. And so for this I like to just draw a circle. Sometimes if I'm doing a problem I'll just draw this off to the side just so I can keep track of my angles. And this circle is defined such that as we move counterclockwise along the circle, we're increasing our angle theta. And the different axes on this particular circle are cosine and sine. So how does this help us? Well, if we're at an angle of 0, we're evaluating something that is on the edge of the circle where cosine is equal to 1, right? It's at a maximum, and I should probably set the scale here that these sides are equal to 1. And of course this is the origin. So when angle is equal to 0, this line is flat against the cosine line, so the value of this function is equal to cosine of 1, and sine is at 0. As we rotate to 90 degrees, we have the opposite, sine is equal to 1, and cosine is equal to 0. As we go past it, you can see we get into regions where cosine is negative or sine is negative. And so this is a good way of sort of remembering the quadrants of which our values are. And it's good to remember sort of the limits as well. When we have sine of 0 degrees, this is equal to the cosine of 90 degrees, which is 0. And the sine of 90 degrees is the cosine of 0 degrees, which is equal to 1. Right? You've probably remembered these constants, but it's good to keep them in mind because when we start talking about the limits of our solutions, testing our solutions to see what they look like at the sort of limits of our values, often we're looking at testing the solutions where the angle goes to 0 or goes to 90 degrees. And so just remembering just these numbers is actually very useful for testing these limits in a quick and precise way. And then one last thing I'll remember to point out is I've been clear about labeling these angles in degrees, but of course we have two different units for angles. There's degrees and radians, and the relationship between them is 360 degrees equals 2 pi radians. So the equivalent relationship, for example, sine of 90 degrees is sine of pi over 2, because this is 2 pi over 4. And we'll be using radians and degrees interchangeably. Again, like all physical quantities, it's important to remember what units we're talking about, not just the numbers. So another math skill that's important to develop is how we use ratios when we're evaluating and comparing, say, a change to a certain physical situation. So a very typical question I might ask in class is, how does the gravitational force change between two masses if we change the distance between them? So for example, if we double the distance between two masses. So this can be solved directly by computing the gravitational force in these two cases, but it can be solved a lot faster if we make use of the ratios involved for the different variables. So the first thing is important to write down the relevant equation, which is, of course, going to be our equation for gravitational force. And the magnitude of that force, which I'm going to indicate by these vertical bars, is equal to the gravitational constant, the product of the masses, and the distance between them squared. So again, if I wanted to figure out the ratio of the forces between these two cases, okay, so for example, let's actually switch this to 2 and 1, all right, where the case where we're having a double mass, all right, that's going to be gm1 m2, and I'm sorry, I meant double distance, so that's 2r squared, divided by the original force, which is 1 over r squared. Now again, I can just go ahead and calculate out these numbers and solve for all the different unit conversions and everything like that. But in fact, we have lots of common variables in here, so what I'm really interested in is how just one of those variables change, and that's the distance. So I can simply cancel out our gm1, m2 products because they are the same in both cases. And I can just look at the ratio. That ratio is going to be r over 2r squared, or simply 1/4. So I didn't have to do a lot of math in the end in order to calculate the ratio between these two forces. I just simply had to write out my equation so I can look at just the variables that are changing. Here's another example that uses more than one variable. Let's say I want to look at the ratio between the force between the Earth and Sun, the gravitational force, versus the force between Saturn and the Sun. Now, this is a little more complicated because we're talking about changing both the distances, because the Saturn orbits at a much larger distance than the Earth does, as well as the masses of the objects involved, at least in this case, the planets. But again, by just sticking to this ratio format, I can very easily solve this problem without a lot of thought, or a lot of work. Always a lot of thought. So when we look at how these variables are written down, what we can find is that, of course, the gravitational constant is going to be the same in both cases, so that's not going to contribute. If I use m1 to be the mass of the sun, that's the same in both cases, and so that's not going to contribute. So we're just looking at the ratio of the masses of the planets and their distances from the sun. So I can rewrite this gravitational force ratio as the ratio of the mass of the Earth over the mass of Saturn times, and since it's 1 over r squared, it's going to be the orbital radius of Saturn divided by the orbital radius of Earth. And I apologize for my change in subscript there. These are numbers that we can very quickly look up online. So we know that the mass of Saturn is about 95 times the mass of Earth. And Saturn's orbital radius is about 9.6 times that of the Earth. The unit, by the way, there is astronomical units, and that's the distance between the Sun and the Earth. So the Sun is at Saturn is at 9.6 astronomical units on average. When we calculate this ratio out, we find that it's very close to 1. In fact, it's about 0.97. So what we've learned is that the force between Saturn and the Sun is almost identical to the force between Earth and the Sun. And that's because we're balancing out the different masses and radii. Again, we could have calculated those numbers explicitly, but you can see it's very quickly if we make use of this ratio format in order to look at comparisons between different quantities. The third set of math skills that are important to develop is some basic calculus. Now, the one sequence is an algebra primarily based course, but there's a lot of relationships between variables that really ultimately derive from calculus. Indeed, calculus was a tool that Newton developed when he sort of developed the whole framework of classical mechanics in his Principia. So it's important to at least understand the connections between derivatives and integrals for functions that we're going to see very often. And so it's important to sort of at least remember a few basic derivatives and the integrals that are the reverse side of them. So we'll often see relationships in polynomials. So it's good to know that the derivative of x to some power n, and that n can be any kind of number, is just equal to n times x to the n minus 1. So the derivative of a polynomial reduces that polynomial by 1 power. And related to this, of course, if the power n is 0, that means you have a constant value. That's going to give you a 0 out in front, and that's 0. And so the derivative of any constant number is always equal to 0. That should make sense, because if you have something that's constant, it's not changing. And the derivative is really about change. And so if there's no change, right, the derivative is going to be 0. The other function we're going to see often are the trigonometric functions. We'll see how those change as well. And so it's good to remember how these trigonometric functions operate with derivatives. And in fact, they're great because they operate back and forth. And so the derivative of sine is equal to cosine, while the derivative of cosine is equal to minus sine, right? So these derivatives are going back and forth between cosine and sine with a flip of the sign, which is the sign in this case minus sine, as we do this. Now we'll see cosines and sines when we talk about harmonic motion, and the derivatives are going to be related to position, velocity, and acceleration. And so recognizing this sort of back and forth relationship between sines and cosines and derivatives is important. The last function that we'll see very often is exponents. And those tend to actually have fairly easy derivatives. So the derivative of e to the x with respect to x is just e to the x itself. And the derivative of e to the minus x is equal to minus e to the minus x. So the exponential function is great because it actually derives back onto itself. Now this is really the whole ecosystem of derivatives that you'll need to know, or at least recognize in the Physics 1 course. And just remember that the integrals are the reverse. Right? So the integral, for example, of cosine x is equal to sine x plus a constant. That's an important thing to put in the end. Because we don't know with respect to that one constant, because the derivative of constant is 0, it's possible that we add a constant to this function as we do the integral. So the integral of cosine x gives us sine x plus a constant. The integral of minus sine x goes to cosine x, again plus a constant. Now, part of calculating more complicated integrals is remember that we can sort of carry through this derivation through the function as we proceed. And this is called the chain rule. And this provides a way of evaluating more complicated equations. And in fact, we kind of already did this when we looked at the derivative of e to the minus x. But more generally, if you're taking the derivative of some function that itself has a function of your variable x inside of it, then you're just taking the derivative chain of that function with respect to the thing inside of it, the sort of main variable, and then that main variable with respect to the thing you're actually interested in, which is in this case is x. Now this is very abstract. Let's do an example. So if I want to do the derivative of, say, sine of ax, all right, ax is my function u, and so to actually solve this, I can take the derivative of sine with respect to u, and then take the derivative of u with respect to x. And so this is equal to derivative of sine with respect to u, which we actually already know is going to be cosine. So this is going to be cosine times ax times the derivative of this u, which is a times x with respect to x. That's just this function, x to the n. So that gives us 1 times a constant. So that just gives us an a out in front. Right? So you can imagine we can have some fairly complicated functions in here, but by providing the chain rule, we can actually solve them out fairly straightforwardly. So in addition to being able to do some basic calculus, it's important to see how calculus actually applies graphically when we look at relationships between quantities. And so developing a graphical understanding of derivatives and integrals is important to evaluating these relationships and extracting out some information about the motion. So for example, if I have a particular plot of velocity versus time, I can say a lot about what's going on in this motion without actually having to explicitly calculate the integrals or derivatives by looking at how those evaluate graphically. Now, remember that derivatives are really about change, and integrals are really about sums or accumulation. So when we look at this plot, we can actually identify the derivative of the velocity at any given time by looking at how the function changes as it progresses. And that change, right, how it increases or decreases as a function of time, is really just a measure of the slope of the line. And so if I take a point here and I draw a tangent line to that tangent line, that slope, tells me essentially the derivative of this function. So slope is equivalent of derivative. All right? And on this diagram, we can say at least qualitatively that at this particular point in time, the velocity is increasing, and so its derivative is greater than 0. And in fact, the derivative of velocity with respect to time, as we will see, is equal to the acceleration. And so we can immediately discern that there is an acceleration on this particle, and that acceleration is greater than 0. Now on the other side, the integral being an accumulation tells us essentially how much velocity we've accumulated over time. And that's measuring sort of the total area under this curve. And so if I start at some given time t0 and some later time t1, the integral essentially measures the product of velocity times time over this time period. And so this is essentially a sum over area. This is the equivalent of an integral. And the integral being the opposite of derivative, this is actually going from velocity down one step to displacement. And so the total displacement is equal to velocity integrated over time between these two time steps. All right? So we can use this graph to actually figure out how much an object has moved over a given amount of time by simply adding up the area under this curve. All right? That's an accumulation. Now, one more part of this graph that we can evaluate is the not just the slope of the change, but also the overall curvature of this line. You notice that the line is increasing very fast at the beginning, but then towards the end it's sort of leveling out. So there's a change in the change of the velocity as we proceed with time, and that's known as curvature. And that curvature can also be related to the second derivative. So curvature is equal to the second derivative, which is the change of the change, right? And that's equal to d squared v dt squared And in fact, we have a word for that. That's called the jerk on an object. All right, not a common quantity of motion we talk about, but that does exist. So this measures how much the velocity is changing and how much of the velocity change is changing with time. It's also describing how much the acceleration changes with time. So this might be something we see, for example, in harmonic motion as the object moves back and forth. So being able to recognize the components of motion based graphically on our sort of position versus time or velocity versus time, or even when we start looking at the energy versus position, the derivative of that was going to give us something about the forces acting on the object. These can be discerned graphically from the graph, and you can actually start talking about the motion or behavior of an object based simply on the structure of this relationship. So the last set of math skills to develop is to be able to recognize functional forms between relationships. So this is looking at the graph of, say, one variable versus another and recognize what is the function that actually underlines that relationship. This is a little bit of pattern matching, but it's a good practice to sort of get an idea of how things are related, and that will give you to a place where you can actually identify the patterns and then be able to predict the motion in the future. So this goes back to kind of the three categories of functions that we talked about in terms of basic calculus: polynomials, trigonometric functions, sine and cosine, and exponentials. So we'll just take a quick look at how those functional forms look and how they're compared. So if I take a graph of, say, position versus time as just an example, there's different ways that we can relate different polynomial functions on this. Of course, the most basic one is if you just have a constant value, right? X equals constant. Something that doesn't change in time at all. It's just a straight horizontal line. We can, of course, have more complicated things like, for example, a linear relationship. X equals a times t. So this would be, for example, a case of constant velocity, where the position just changes linearly with time. If we have a constant acceleration, we actually go up another order of polynomial, and that will give us more of a quadratic equation. X equals a t squared. Right? And you can imagine what x equals t cubed, t to the fourth. This will get steeper and steeper as we go up. Now, another important relation is something that's an inverse relationship, so something that changes as 1 over time, for example. That's going to be more of a curve that comes in this way. So this might be xo is equal to a over t. Right. These different relation forms are important to recognize because it allows you to sort of make some predictions about the motion. You can also check whether the limits of these relationships are consistent with the motion that you see. So in the case of position versus time, where it goes over 1 over t, the result as you go to time equals 0 is that you would have an infinite position. So if that makes sense physically, then maybe that's your relationship. If it doesn't, you have to think of another relationship. Another set of relationships are our harmonic functions, or our sine and cosine. So again, let's look at position versus time. And in fact, I'm going to set my 0 up here in the middle, as you'll see why in just a moment. Now, sine and cosines are harmonic functions, and that means that they repeat over time. And so I'm just going to show one cycle of the motion, but keep in mind that this is going to keep going over time. So a sine function, if you remember that sine of 0 is 0, so that function has to start at our origin. And as we went around that circle, it increases up to a maximum. So our sine function actually looks something like this. Right? So if we write that down as x equals a times sine, let's say, times omega t, which is a very common form that we'll see a little bit later, these terms provide us some way of mapping out what the shape of this particular function looks like. A is the amplitude of this curve, and so its maximum and minimum values are a and minus a. So you can figure out that constant out in front right away. Whereas the cycle here happens over 2 pi, so sine of 0 is the same exactly number as sine of 2 pi. They're both 0. And so this point where you get back to 0 again at the end of your cycle is just equal to 2 pi over omega, because 2 pi over omega times omega gives us just 2 pi, and that's a full cycle. So with just some basic mapping of the curve, we can actually write down in detail what the functional form of this relationship is. The other side of this is cosine, and that starts at the maximum value and proceeds down to 0. And so it's slightly offset from our sine function, but has the same basic structure. All right. Again, it's one cycle. It happens in 2 pi over omega time. Its amplitude is based on the coefficient out in front. So if you see, again, a function that starts at 1, that might be a cosine relation. If you see a function that starts at 0, that might be a sine relation. Finally, the third set of relationships we have, again, if we plot time versus position, is our exponential functions. And these can come in very different forms. If you have a positive exponential, that's something that starts, say, at 1 and increases dramatically over time, or it starts at some constant. So we'll label that constant a. This is the function x equals a e to the, well, let's call it alpha t. All right? Again, these are just constants, but the constants tell us something about the behavior of this particular motion over time. Because it increases exponentially with time, this is just going to shoot up to infinite in some finite amount of time. But it starts at some finite value, which is the constant out in front here. This is very different than, for example, the x equals a t squared here, where it does increase rapidly but doesn't just shoot up as quickly. Exponentials tend to have a much more rapid rise rate. And so if you see something that really increases fastly, it might be more of an exponential than a polynomial relation. The opposite of this would be one where you have a declining function with time, right? Something that starts at a and then drops down to 0. That's going to be something that has a negative exponent in the exponential there, minus alpha t. So as we get to t very large, this number becomes 1 over a big number, which tends to 0, so eventually this function peters out to nothing. Right? That's, again, a behavior you might see, for example, as things are slowed down by friction. And a related expression might be if we start at 0 and we move up to some limiting value. So that might look like this, where that limiting value is right here. Right? This is kind of almost the opposite of this declining exponential. And we can write down that function as x equals, let's call this b as a new number, 1 minus e to the minus alpha t. Right? A slightly more complicated expression, but it's kind of conveying the same sense that over time we sort of approach a finite value. In this case, not 0, but it's equal to b. So you may see this behavior in different motions. It's good to sort of recognize what function those motions correspond to, because it gives you a very quick way of writing down the solution to a problem, and then you can start experimenting with what the different variables are in that solution. So in summary, there are at least 5 basic math skills that I encourage you to develop and practice for the Physics 1A course, and indeed for all the physics courses that you'll be taking here at UCSD. The first is to really understand your trigonometry, know your trigonometric relations. This doesn't necessarily require knowing the sort of complicated trigonometric relation between sine squared and cosine and tan squared, but know those definitions for sine, cosine, and tangent, and their limits, where the angle goes from 0 or goes to 90 degrees, for example. Make sure you make use of ratios. This will greatly simplify your calculations. Instead of going and calculating a complicated formula, you can just look at the variables that change, and that might provide an answer without having to do a lot of rigorous math work. Make sure you know your basic derivatives and integrals of functions that we see commonly in physics. Those include polynomials, the harmonic equations, sine and cosine, and then also the exponential relations, e to the x and e to the minus x. It's important to develop a graphical understanding of derivatives and integrals, and more generally of change and accumulation, because we'll have lots of examples where we show these relationships, for example, position versus time or energy versus position, and you can get an idea of the motion or the physics of the system by just interpreting the sort of shape of that relationship. And finally, it's important to recognize just general functional forms when you're looking at relationships between physical variables. And that goes back to our polynomial, sine, cosine, and exponential functions. Again, these are the most common functions we'll see in our Physics 1A course. And if you can learn to recognize what those functions look like when you plot 2 variables against each other, you can come up with a fairly quick idea of the solution to a problem without having to memorize all sorts of complicated equations. So again, I encourage you to develop and foster these techniques because you'll be using a lot of them in the next quarter and indeed throughout the physics course sequence.